All right, in this video, we are going to talk about the graphs of the logarithmic function. Um, first, if you haven't watched any of the previous videos where we talked about how to work with logarithmic expressions, you need to go watch those videos. So remember, the base of a logarithm has got to be a positive real number and not equal to 1. And so if that's the case, then the logarithmic function base b of a real number x is defined by this. Again, in the previous videos, we talked about what this expression means and how to calculate these things both by hand when it's feasible to do that, and also with the calculator in the case of log base 10 and the natural log, which is log base e. All right, so all of these functions, right? This is not just one function, but a bunch of different functions, right? For every base b, there's going to be a different logarithmic function, but they all kind of look fairly similar to each other for the most part. So first off, the domain of any of these logarithmic functions is 0 to infinity. So over here in Desmos, I've graphed out what that looks like. And you can see when you graph out this is log base 2, you can see that there's no graph over here to the left of the y-axis, and that's the same for all of these functions that we're going to talk about. The domain, right, is all positive real numbers, so there is no graph over here at all. Okay, so it's only from 0 on out, and that's not including 0 either. All right, the range of these logarithmic functions is all real numbers, right? So no matter where what number you have, like for instance 8 right here, you can find some point on the graph, right, that has 8 as a y-coordinate. Now you might have to zoom really, really far out, okay, in order to do that. All right, so I'm not going to do that, but eventually, right, it will get there, and we can it would be 2 to the 8th, right? Power. If I punch that in, right, I will get an 8, right, as the output. And similarly, right, if, whatever number, if you say for instance 5, right, you want to know, is that in the domain? Well, if you just plug in 2 to the 5th into this function here, you're going to get a 5 out. Right? And we can always do that no matter what real number we're talking about. So the range is all real numbers. The graph of these logarithmic functions does keep going up and up, right? You might say, looking at it, it kind of looks like functions that we talked about earlier that have horizontal asymptotes, but these logarithmic functions do not have horizontal asymptotes. The value of this function gets bigger and bigger and bigger, okay? It's just that they do it really, really slowly. So this graph just keeps going up and up, right? It's just very, very slow. So if you plug in a pretty big number, right, into this log function, you can see that the y value is only 26, all right? So that's one of the kind of peculiar things about the logarithmic functions. The x-intercept of any of these log functions is 1, 0. That's this point right here. And I can graph out a couple of other log functions so you can kind of compare those. So if I do log base, let's say 5, that's what it looks like. And if I do log x, which is log base 10, and then if I do ln x, which is log base e, you can see they kind of all look the same. They're just a little lower or higher depending on where you are. But they all kind of have that same basic shape, and they all go through this point right on the x-axis, and that's 1, 0. So that's the only x-intercept of a logarithmic function. There are no y-intercepts on these logarithmic functions, right, because of the fact that 0 is not in the domain. If I try to plug in 0 into any of these functions, right, you're going to get that it's undefined for no matter which logarithmic function you do. Okay, and same thing for a negative number. There, though, it's slightly different in the sense that you'll get a complex number. But remember, our class, we're only talking about functions where you plug real numbers in, and we want real numbers for the outputs as well. Okay. We can have logarithmic functions with bases that are in between 0 and 1. So if I did k of x equals log base, nope, I guess I'll do it log base 0.5. All right, and so you can see what that looks like. All right, and so with log base 5, all those properties hold except for this part right here, right? If the base is bigger than 1, then your logarithmic function is going to be increasing on its domain. If the base is in between 0 and 1, then it's going to be decreasing, right? It'll go like this and start decreasing out, okay? One other thing that I want to point out about all of these logarithmic functions is that they are inverses, right, of the exponential functions. So for instance, if I take a look at this graph, ln x, and the graph of e to the x, right, and graph it about the line y equals x, you can see that the function ln x, right, this green one, and the purple one, e to the x, right, their graphs are symmetrical about this line y equals x. If you remember back to when we talked about inverse functions and the relationship of a function, a one-to-one function with its inverse function, it was that exact same relationship. And so, right, the logarithmic function is the inverse of the exponential function and vice versa. Okay? And we can illustrate for all of those as well. So for instance, if I do log base 2, its inverse is 2 to the x, right? And you can see that those graphs are symmetric about the line y equals x. The inverse of log base 5 of x is going to be 5 to the x. And the inverse of the common log, which is log base 10, right, is 10 to the x. You can see that once again that is symmetric, right, about the line y equals x. All right. So that's essentially a really close relationship between exponential functions and logarithmic functions. They are the inverses of each other. So later on, we will be solving equations, logarithmic equations and exponential equations. So what you're going to do is use the inverse function to solve equations containing whichever of the type of functions the equation has, like logarithmic or exponential. All right. So next up, what I want to talk about is finding the domain of other logarithmic functions. So these logarithmic functions are basically transformations of the original logarithm graphs. Though they show up pretty frequently when we'll talk about solving logarithmic equations. So in order to find the domain of a transformation of a logarithmic function, what you would do is set the inside part of the logarithm greater than 0 and then solve that inequality. All right, so if you remember earlier in the class when we talked about the domain, we said there are some things that you need to check, right, when you're finding the domain of a function. One is the division by 0 problem. The second is the even root problem, right? And so now this is a new third issue, right, that you'll need to take care of when we are talking about finding the domain of functions. If you have a logarithm, right, as part of your function, the inside part must be greater than 0. So what you would do is just take the inside part, set it greater than 0, and solve the inequality. All right. Okay, so let's take a look at this problem here. And just give me a second while I write this problem down. Okay, so f of x is log base 2 of 5x minus 6. All right, they are asking us to find the domain of this function, okay? So all we need to do, right, is to take this inside part right here and set it greater than 0. Okay. Now, if there are other issues with a domain, like fractions with variables in the bottom part, or even roots, we'd have to, take those into account as well. But right now, just trying to keep it simple and only focus on this log issue. Okay. So just take the inside part, set it greater than 0, right? And the reason why you're doing this, right, is because, right, the domain of the logarithmic function, the regular logarithmic functions, are all positive real numbers. So in other words, right, the inside part right here, which is 5x minus 6, has to be greater than 0, right? That means it has to be positive. All right, and you solve this inequality out, and that will be your domain, okay? All right, so to solve this for x, this is a linear inequality, so I just get x by itself. I would add 6 to both sides. And so I get 5x is greater than 6. All right, and then divide both sides by 5. So get x is greater than 6/5. Okay. All right, so I've solved that inequality. Don't forget, right, if you are dividing through by a negative number, we didn't do that here, but just it's a common mistake, right? Make sure that you flip the inequality signs on here. So the domain, right, of this function in interval notation would be written as 6/5 to infinity, right? All the x's that are greater than 6/5. And it would be a parenthesis on the 6/5, right, because of the fact that there's no or equal to, right, on this inequality. So, and of course, infinity or minus infinity in our class is always going to get the open parenthesis. All right, and so that's it on this one. If I graph this out, log base 2, 5x minus 6. You can see, right, what the domain is. It is all real numbers past this point right here. That point, right, where the asymptote is y equals 6/5, right? So you can see there's only the graph over here to the right of that line, x equals 6/5. Okay. Okay, the next example is find the domain of the logarithmic function f of x equals ln of x squared minus 3x All right, so again, we have a logarithmic function. We want to find the domain of it. Well, with logarithmic functions, the inside part of the log, right, what you're taking the log of, you set it greater than 0 and solve that out. Okay, so this inequality, right, is called a quadratic inequality. It is a more complicated inequality than the previous inequality that we just solved. All right, you cannot solve it the way that we solved the previous one. So to solve this quadratic inequality, right, and how can I tell that it's quadratic? I can tell that it's quadratic, right, because it has this x squared. In the previous example, right, that was a linear function. This is a quadratic. So to solve a quadratic function, right, what you would need to do is to replace the inequality sign with an equal sign, all right? And solve the equation first. All right, so this is just a quadratic equation now. We've already talked about how to solve those. This one happens to be one of the easier types. It's easy because there's no constant term in here, okay? All right. So if there's no constant term in there, we can factor out the x, and that's the first step in factoring, is to factor out the greatest common factor. So looking at x squared and 3x, right, they have a common factor of x, pull it out, and I'm left with x times x minus 3 equals 0. Well, if I multiply x and x minus 3 and I'm getting 0, well, that means that either x is 0 or x minus 3 is 0. Okay, and then I would solve each of those. Okay, so when you get those two solutions like this for a quadratic inequality, right, it's not enough to just say, okay, 0 and 3, because there's a lot more solutions than just 0 and 3. What you need to do is to take those numbers and put them on a number line. All right. So I put those numbers on the solutions that I get from the equation on a number line. That's going to break the number line up into 3 pieces. This piece over here to the left of 0, this piece over here between 0 and 3, and this piece over here to the right of 3. All right, and what you need to do is to pick some test points on each one of those pieces. So on this piece over here to the left of 0, I'm going to pick -1. On this piece in between 0 and 3, I'm going to pick 1. And on this piece over here to the right of 3, right, I'm going to pick 4. All right. So what I am going to do is I am going to take those test numbers and I'm going to plug them into the original inequality and see what I get. All right. And if I get a true statement, that means every number on that piece is a solution of this inequality. Okay. All right, so I'm going to take this -1 and I'm going to plug it into this inequality. Up here, I get 1 plus 3 is greater than 0, so 4 is greater than 0. All right, it is true that 4 is greater than 0, right? And so what that means is -1 is a solution of this inequality, right? And it's all or nothing on each piece. So that means that all of these numbers over here to the left of 0 are solutions. Okay. Next up, I'm going to test this 1. So I'm going to take the 1 and plug it into the inequality. So when I plug a 1 in, I get 1 minus 3, which is -2. So I get -2 is greater than 0. Well, that's not true. That's false, right? So that means 1 is not a solution of this inequality. That means none of the numbers in between 0 and 3 are solutions. All right, next up, I'm going to check 4. So I'm going to take 4 and plug it into this original inequality. When I do that, I get 4 squared minus 3 times 4. It's greater than 0. 16 minus 12 is greater than 0. So 4 is greater than 0. That is a true statement, right? And so the answer here is yes, right? These numbers over here to the right of 3 are solutions of this inequality. Okay, so now we have all of the solutions of the inequality. It's all the numbers to the left of 0 together with all the numbers to the right of 0. So to write the domain, right, in interval notation, right, first I would start off with this piece over here to the left of 0. To write that little piece in interval notation, it would be -infinity to 0. This piece is not in the domain. These 0 and 3 are not in the domain either, right? Because those will be places where the inside is 0, right? And ln of 0 is undefined. You can't have that, right? So the only other solutions are these solutions over here to the right of 3, right? And if you want to write that piece in interval notation, it would be 3 to infinity, right? With parenthesis indicating that the 3 is not included in there. Okay, so that's this piece here. And then you would just connect those with a union symbol. Okay. All right, now you may say, hey, that seems complicated compared to the last one. It is complicated, right? But any nonlinear inequality, right, is going to be more complicated than the linear version, generally speaking. Okay. The only ones that you can solve using the method of the previous example are the linear ones. All the others, right, you have to use some more complicated method like this one right here. All right. Okay. So let's take a look at the graph of this and just verify that on the graph. So it's ln of x squared minus 3x, right? And here you can see, right, we had the piece to the left of 0, that's this piece over here, and we had the piece to the right of 3, that's this piece of the graph over here. There is no graph, right, in between these two pieces, okay? There's nothing in here, and the only reason we know that is because, right, that's what the math says. When we calculate the domain, right, we get no solutions in here. That means that there is no graph here. It's not just a matter that we didn't zoom out enough or zoom in, zoom out up or down enough. There is no graph here. It doesn't matter how much we zoom out. We're not going to see anything between these two branches of the graph. All right. Okay, that's it for this video.